The question is, could you explain the algebraic or the component method of finding the resultant of two forces in 2D? Just to have a big picture on this topic, remember our related discussion on another video. In a broader sense, there are two methods of finding the resultant of forces. The first one is called the graphical method. The second one is called the algebraic method, which is also called the component method, the mathematical method, and sometimes called the Cartesian vector method. So this question has to do with the second method, algebraic method. In fact, we touched on the fundamentals of this method as part of the triangle method we discussed in one of the earlier videos. Remember, as we went through the proof of the triangle method, we talked about representing a vector by its components, right? That's the basis for the algebraic method. So let's talk about it. Say we are interested in finding the resultant of two forces F1 and F2 shown in this picture. Within the framework of vector operations, finding the resultant of two forces is nothing more than adding the vectors representing the two forces. Alright, so in this algebraic method, the first thing we want to do is to represent the force vectors in their component forms. Remember, we discussed this in an earlier video, right? We want to find the projection of these vectors along the x and y axes. To achieve this, we do a little temporary construction like shown in this picture here. To find the projections of F1, we draw a little triangle like shown here. So you want to make sure you put the arrows in the correct directions, right? Similarly, to find the projections of F2, we complete this triangle. Say the absolute values of these distances are A, B, C, and D. Then we see the x component of F1 is A, the y component of F1 is B, the x component of F2 is C, the y component of F2 is minus D because the arrow is pointing downward. Denoting the x component of F1 as F1x and the y component of F1 as F1y, F1 then is F1x times I plus F1y times j, where F1x is A and F1y is B. You write F2 in a similar form. We find the resultant of F1 and F2 by adding the two force vectors. Utilizing the component form of these vectors, F1 plus F2 can be written like this. In the next line, what we do is we collect all the I terms and group them together. So here we have F1x and F2x go with the I term, right? So group them together, that means sum them up, and then put that along with the unit vector I. Do the same for the y component. So that will be F1y plus F2y multiplied by the unit vector j. In other words, the vector f, the resultant vector, which can be written as this, right, fx times I plus fy times j, is given by this expression. Now equating the terms that go with a particular unit vector on either side of the equation, we get this. Fx equals f1x plus f2x, fy equals f1y plus f2y. You can see that this method can be extended to a problem involving any number of vectors like f1, f2, f3, f4, and so on. To find the resultant of these multiple vectors, all we have to do is to add them together. So adding means you add up the x components, and that's going to be the x component of the resultant vector. Similarly, you sum up the y components of these vectors, and that's going to be the y component of the resultant vector. So at this point, your resultant vector will be in a form similar to this, right? There's going to be a number multiplied by I plus another number multiplied by j. Remember, in the most fundamental way, a vector has a magnitude and a direction, right? So to complete the problem of finding the resultant, you want to go a step further and find the magnitude and the direction of the resultant vector. So what you want to do is, based on the numbers, you want to make a sketch of the resultant vector. So that way you will know whether the vector plots in the first quadrant, second quadrant, third quadrant, or the fourth quadrant. This allows you to define the direction in an unambiguous manner. Alright, so in this first example, it's fairly straightforward. We have a positive x component, which is 4, right? And we have a positive y component, which is 3. And therefore, your vector f plots like this. The magnitude is the length of the vector, right? Which by Pythagorean theorem is square root of 4 squared plus 3 squared. So we get a value of 5 for the magnitude. The standard method of representing the direction is to use this angle theta, which is measured in the counterclockwise direction from the positive x-axis, right? So let's go ahead and find that angle. Theta, by looking at this right triangle, is tan inverse of 3 over 4. So we get a value of 36.9 degrees for that. And therefore, the direction is represented by theta, which is 36.9 degrees. Let's look at this example. Example number 2. F is 6i minus 8j. Now you want to sketch this vector, keeping in mind that it has a positive x component and a negative y component, right? So you can see the vector plots in the fourth quadrant. Now considering this right triangle, this distance is 6, which is the x component, and this distance is 8, which is the absolute value of the y component, right? So the magnitude, which is the length of the vector, is once again by the Pythagorean theorem, is 6 square root of 6 squared plus 8 squared. We get a value of 10 for that. To define the direction, you want to do this in 2 steps. First, you want to find an angle that is associated with this triangle. So let's say alpha. Let's go ahead and find alpha, right? Tan alpha is 6 over 8, and therefore alpha is tan inverse of 6 over 8. We get a value of 36.9 degrees again for that, just like the first case, right? Let's also go ahead and find this angle beta. Beta would be 90 minus alpha, which is 53.1 degrees. The standard way of representing the direction would be to use this angle theta, which is measured in the counterclockwise direction from the positive axis. So that will be 360 minus beta, and we get 306.9 degrees for that. Another way of representing that would be to measure an angle in the clockwise direction from the positive x-axis. So that will be minus beta, right? In other words, minus 53.1 degrees. So you could say either the resultant is 10 units at theta equals minus 53.1 degrees, or the resultant is 10 units at theta equals 306.9 degrees. Either one is acceptable.